Good day to everyone. So in the last video, we have discussed about the Euler's method, the derivation of Euler's method using from the Taylor series, and we have also seen some example problem. So in this video, we are going to again discuss about this couple of problems and how to solve the differential equation using the Euler's method. Okay. So the problem one is, so using the Euler's method, we have to numerically integrate the following differential equation: dy by dx is equal to minus 2x cubed plus 12 into x squared minus 20 times of x plus 8.5. And the initial we have to integrate this equation from x is equal to 0 to x is equal to 4 with a time step of 0.5. So the initial conditions are given is at x is equal to 0, the value of y is equal to 1. So we have to compare the numerically obtained answer with the exact solution. Also, we have to repeat the same computation using the time step of 0.5. So initially, you have to do with the time step of 0.5, and then with the 0.25. Then you have to compare both the results, and you have to find out what is the error between the two. Suppose if you are varying the time steps from 0.5 to 0.25. Okay. So we look at the solution for this problem. So solution, we already know this. First we should look at the exact solution. So the exact solution of the above equation can be written as y, which is equal to minus 0.5 x power 4 plus 4 x cubed minus 10 x squared plus 8.5 times of x plus 1. So this is the exact solution of the corresponding differential equation. So we have to find out what is the numerically comparison method, and you have to compare with this exact solution. So first we have to start with the time step of h is equal to 0.5. So we already know the Euler's equation y of I plus 1, which is equal to y of I plus the function of x comma y times of h. So this is the initial the Euler's method. So we already have this initial value I equal to 0. So I 0, we know that the f of x comma y is a slope. So that is the right hand side of this equation, and h is a 0.5 we have taken. Okay, so first we have to find out when y of 0 is equal to 1, that means the initial condition is equal to 1, and we have to find out what is the slope of f of x comma y, and the slope at x is equal to 0 is, you can just substituting this value, you can just find out the x comma y. By substituting the values of x comma y, you can find out the slope f of 0 comma 1, which is equal to so you can just substitute the values of a x value in this equation. So you can get the value of the slope minus 2 times of 0 cube plus 12 0 squared minus 20 times of 0 plus 8.5. So everything is will be 0, so that y accept the 8.5. So the slope of f of 0 comma 1, which can be written as 8.5. So we found the slope of this equation Euler's method, so that you can directly substitute the values here. Therefore, f of 0 comma 0.5 at f equals to 0.5, you can write it as the previous value is, we already know the initial value is 1.0 plus the slope value 8.5 times of the time step. Time step is 0.5. So once we do the value, the final value is 5.25. So that is my f of 0.5 value. That means the value at the time step of 0.5. So we have to just compare this value with the the true value. That means they can just compare with the exact solution. Suppose if I substitute the values of x is equal to 0.5, so you can substitute, we can find out the what is the exact solution with, and what is the difference between the exact and the numerically calculated solution. So the true solution is at x is equal to 0.5 is, so you can find it just substituting the values of 0.5 in this true solution, the exact solution. You can get x is equal to minus 0.5 times of 0.5 the whole power 4 plus 4 times of 0.5 cube minus 10 times of 0.5 the whole square plus 8.5 times of 0.5 plus 1. So this is a, suppose if you do the calculations and the final value of y is equal to 3.21875. They have to write as much as accurate as possible, suppose with the fourth and fifth decimals, so that suppose if the error is very minimal, you can easily calculate. So whenever you are doing the numerical computation, you have to write the answer as accurate as possible. Okay, so we have the exact solution, so that we can easily find out the error. So the error is, the estimated error ET, which is equal to the true solution minus the numerically calculated solution. So 3.21875 minus the calculated value is 5.25, which is equal to minus 2.03125. So that is the estimated error between the exact solution and the numerically calculated solution. So what we are going to do is we are going to do the second step. That means we are going to find out the solution of the dy by dx at the time step of 1. That means we are incrementing the time step by 0.5, so that we are going to find out the y of 1. So for the second step, at y of 1, which is equal to the previous value y of 0.5 plus the slope of f of 0.5 comma y value 5.25, which we have calculated. That means f of xy. The x value we are going to calculate the value of 0.5, and the y value is 5.25, which we have calculated here. So that is what the slope is, and then multiply with the 0.5. The time step, so that I can write the value at y of 0.5, which we have calculated is 5.25 is the previous value, plus the slope which we can calculate again, just substituting the values in this equation on the right hand side with the x is equal to 0.5. Okay, so we can just substitute the values of minus 2 of 0.5 the whole cube plus 12 times of 0.5 the whole square minus 20 0.5 plus 8.5. So this is the slope multiplied by the time step 0.5, and the final answer is y of 1, which is equal to 5.875. So this is the value at the second step. So that we can again find out the error. So that means you can first find out the true solution. So the true solution at x is equal to 1 is, so you already know the exact solution, y is equal to minus 0.5 of times of 1 the whole power 4 plus 4 times cube minus 10 times of 1 power square plus 8.5 times of 1 plus 1. So the final value of y, which is equal to 3.0. So this is the true value, and the calculated value is 5.875. So the error is ET, which is equal to 3.0 minus 5.875. So that is equal to around minus 2.875. So that is my error for the next step. Similarly, you can do the third step at the where we're just incrementing the value by 0.5. So for the third step, so this time you have incremented the value of 0.5 so that your value is 1.5, which is equal to the previous value y of 1 plus the slope at 1 comma 5.875. So that is the value which we have calculated the previously. So that is the slope which we are going to use, and with the multiplied by the time step 0.5. So the previously calculated value is 5.875 plus the slope. Again, you can just write the right hand side of the equation, minus 2 x value is now 1.5 cube plus 12 times of 1.5 squared minus 20 times of 1.5 plus 8.5 multiplied by the time step, and the equation the solution is y of 1.5, which is equal to 5.125. Okay. Now again you can easily calculate the true solution again at this point. At x is equal to 1.5 is, which take y is equal to minus 0.5, 1.5 times of 4 plus 4 into 1.5 times of cube minus 10, 1.5 times squared plus 8.5 into 1.5 plus 1. So the final value y is equal to 2.21875. So this is the exact solution. Now you can again calculate the truncation error. The error is, so this exact solution ET is equal to 2.21875 minus the calculated value 5.125, and the final value which is equal to minus 2.96025. Okay. So similarly, you can add this. You can do the fourth step and the fifth step up to x is equal to 4, and the result is given by suppose I can give the that means you can increment the h step every 0.5, and up to you can find out the values of this solution, numerically find out the solution up to x is equal to 4, and the final value, that means the table of the final values of the the numerically calculated value and exactly calculated value can be given by. So this is the true value which is given here, and the numerically calculated value is the Euler method is given here, and this is the time step. So we have calculated up to 1.5. We got the final value is 2.21875. That's a true solution which we have calculated, and the numerically calculated value is 5.125. That is what we have got here. So that if you continuously do this for the every increment of 0.5 in the time step, you can get the solution for the exact solution as well as the numerically calculated solution, so that you can easily find out the error between these two. Okay, fine. Now what we are going to do is I am going to do the same computation with the time step of h is equal to 0.25, and then I am going to compare the results with the time step of 0.5. So at x is equal to 0, y will be equal to 1 with the time step of 0.25. For the first test time, for the first step, so you have to repeat the same calculation with the just changing the value of h is equal to 0.25. So the first value f of y of 0.25, which can be written as y of 0 plus the function f of 0, 1 with the time step of 0.25. So we already know this value of, we have to find out the value of solution f of 0, 1, which we already found this 2 times of cube plus 12 times of 0 squared minus 20 times of 0 plus 8.5. So the f of 0, 1, which is equal to 8.5, which we have already calculated. Just substituting this into this equation, therefore of y of 0.25, which is equal to the first value, initial value is 1.0 plus 8.5, that's the slope value. 0.25 is the time step, so that the final value of y of 0.25 can be written as 3.125. So this is the numerically calculated solution at the time step of 0.25 for the first time step. Now I can write the exact solution. This is the true solution using the exact formula at x is equal to 0 with x is equal to 0.25. So I can write y is equal to minus 0.5 times of 0.25 to the power 4 plus 4 times of 0.25 cube minus 10 times of 0.25 squared plus 8.5 times of 0.25 plus 1. And you can do the calculations, and the final value is y is equal to 2.56054. So this is the exact solution for the time step of x is equal to 0.25. Now we can find out the error ET, which is equal to the exact solution 2.56054 minus the calculated value, that means 3.125. The final value, which is error is equal to minus 0.56446. So this is the error which we have obtained. So you can just compare this error with the calculated error in the previous value ET for the h is equal to 0.5 minus 2.03125. So this is the error which we have obtained when using the time step of h is equal to 0.5. Now the error is actually minimized when you are using the 0.25, so that the error is minus 0.56446. Okay. So similarly, you can numerically find the solution at the second step. So the second time step at x is equal to 0.5 with the y value of 3.125, which we have calculated using the previous method. Okay. So similarly, just substituting these values in the Euler's equation, y of 0.5, which is equal to y of 0.25 plus the slope of 0.25 comma 3.125 x and y values multiplied by the time step 0.25. The value is, you can just substitute in this value 3.125 plus minus 2 times of 0.25 the whole cube plus 12 times of 0.25 squared minus 20 times of 0.25 plus 8.5. This is a slope multiplied by the 0.25. So the exact value is 4.1796688. So that is my y of 0.5 value. Again, I can calculate the true solution. The true solution at x is equal to 0.5 is, so y is equal to minus 0.5 multiplied by the 0.5 times of 4 plus 4 times of 0.5 cube minus 10 times of 0.5 squared plus 8.5 times of 0.5 plus 1. So the final value y is equal to 3.21875. Now I can calculate the error again. The error ET, which is equal to, that is the calculated value, the true value 3.21875 minus the calculated value 4.1796688. So the value is minus 0.960938. That is the error which we have calculated. So when you are using h is equal to 0.5, the error which we have calculated is minus 2.875, but that means when h is equal to 0.5, now we can see that the same time step, the error is actually reduced to minus 0.96938. So similarly, you can do the same repeated arithmetic operations for up to x is equal to 4, and you can just compare the result. So what I have did is I have just written the program. Suppose if you want to do this for the whole length of x is equal to 0 to some value, so you have to manually do this repeatedly. So that means the same progress you are doing with the repeated time step. Otherwise, you can do the, you can write the code, Fortran code, and then you can do this the arithmetic, the integration. So this is a program. In this, I have written the code to solve the true solution, to find the true solution, as well as the numerical approximation using the Euler's method, which we have seen in the previous video. I have used the same time step, only I just changed the slope value using this 2x squared, minus 2 times of x cubed plus 12 times of x squared minus 20 times of x plus 8.5, and then I can just integrating this using the Euler's method, and this the answer is actually saved in the data files here, and I can easily plot these values for the value h is equal to 0.5 first. First, I can just plot the analytical, the exact solution, and I can compare it with the numerically obtained solution for the h is equal to 0.5, and the result is plotted here. Here, this the purple line is actually exact solution, and this green color is the numerical solution for h is equal to 0.5. So you can see that initially this both are having the same value of 1, which we have calculated, and the value is given here. So once if you are increasing the time step, then going further, then you can see this the exact solution and true solutions are exactly not mismatching. There is an error, and this error is actually, you can see here. So the first time step of 0.5, this true value is around here. However, the calculated value of numerical solution is almost here. This is the error. So this error is actually further growing, and so even though there is an error between this numerically calculated solution and the exact solution, you can see that this numerically calculated solution is actually at least trying to find out the track of the solution. You can see this is the exact solution which is flowing, and this is actually almost tracking the numerically calculated solution, the exactly calculated solution. However, we can see the error. So the one possible method to reduce this error is just reducing the time step h is equal to the further, so that we have already calculated the solution for the h is equal to 0.25. So I'm going to just changing the values of h is equal to 0.25, run the program again, and then we can save the exact solution data in the another file. Then I can replot it, which is plotted here. Here again, this is the exact solution, and this is for h is equal to 0.5, and this one which is actually plotted for the h is equal to 0.25. Now you can see this, the error is actually almost reduced significantly, and the track is actually exactly following the exact solution. However, you can see the minimum error is actually occurred, but however the error is actually reduced from the time step which we have used in the h is equal to 0.5. Here you can see that you are actually integrating this equation for the first time step, which is the initial condition, and the next time step is actually started at here for x is equal to 0.5, so that it is actually just finding the slope. That means it's actually plotting a straight line. This straight line is actually meeting the point of 0.5 at this point, so that this may be taken as the slope. Okay. However, if you are using the 0.25, you are actually dividing this 0.5 into 2 times, so that if you are just at this point 0.25, where if you plot the slope, it is actually just meeting this point at this point, so that it is actually taken as a solution, the numerically calculated solution. And from this solution, you can again find the slope, which is actually the 0.5. That is actually much accurate than the previous one. So similarly, if you further reduce the time step h further, then you can get the numerical solution is very close to the exact solution. So in this figure, you can see that this yellow color line is plotted for h is equal to 0.1, and this is for 0.25, and this is for 0.5. Now you can see this once if I can use the same method, only difference is I have just reduced the time step as 0.1, so that you can see that the numerical solution is almost following the exact solution. However, again you can see the error. Further, if you reduce the time step, say h is equal to 0.01, you can obtain the results as shown in this figure, where this yellow line is actually plotted for h is equal to 0.01. You cannot able to identify the difference between, you cannot able to even identify the exact solution and the numerically calculated solution. That means the numerically calculated solution is exactly tracking the numerically calculated solution exactly for calculating the real solution, the true solution. However, you cannot able to identify the error at this view. However, if you zoom this plot with some the point, for example, if I zoom this plot, so I can see the error between the calculated value of h is equal to 0.01. This is the exact solution. So still there is a error. So that even if you are further increasing the h equal to 0. Further decrease the time step, then you can get the true solution. However, suppose if you want to reduce the time step for very small values, the computation time required for this solving this problem will be drastically increased. So that what is our aim is, you have to find that solution, numerical solution, with the minimum time. So that what we have to do is, we have to move from the first order approximation to the second order approximation, or you can go for the higher order methods to find out the solution with the even for the nominal the correct value of h for the time step. Okay, so we can see the one more problem. So the second problem is, we have to solve the initial value problem, y into dy by dx is equal to x, and the initial value is given at x equal to 0. So value of y is equal to 1. So you have to use the Euler's method to solve this problem from the range of x is equal to 0 to 0.8 with a time step of 0.2 and 0.1. So you have to do for the two different time steps, h is equal to 0.2 and h is equal to 0.1. Then you have to compare the results with the exact solution at time at x is equal to 0.8. Okay, so the value of dy by dx, which is nothing but the x divided by y, which is our x of y, the f of the function f of x y, and the initial condition which is given as x is equal to 0, y equal to 1. So this is the initial condition, and we already know that the Euler's method. So at h is equal to 0.2, which we are going to calculate first. So Euler's method of y of I plus 1, which is equal to y of I plus the slope is actually given as x divided by y, that means xi divided by yi multiplied by the time step h. So that I can just substitute this, I can find out the value of y of 0.2, which is equal to, taken as y1, that is I can take this as y0, that means the initial value plus x0 divided by y0 multiplied by the time step, which is equal to 0.2. And so I can just substitute in the value of y0, which is equal to 1, and so the value of x is equal to 0 and y equal to 1, so this value will be 0. So your value of will be equal to 1, that is y0 value is 1. So I can just substitute the values y1, and this value will be 0, so that you will get the y1 value is 0. So that is the solution for the y of 0.2 point, and I can find out the point at 0.4, is equal to, taken as y2. Then you can again substitute the values of y1 plus 0. So x1 divided by y1 into 0.2, which is equal to the y1 value is given as 1 plus 0.2 times of x1 value is again now taken as 0.2, that is the difference, divided by the 1.0, that means the y value. So the value is given as 1.04. So this is the value of y at the point of y of 0.4. Similarly, I can calculate the y of 0.6, which is equal to, taken as y3, which is equal to y2 plus x2 divided by y2 divided by 0.2. So y2 value is 1.04 now plus 0.2 into, so the x value, so it is 0.4 divided by 1.04. So I can give the value is 1.11692. So this is the value at where y equal to 0.6, and so y of 0.8 I can calculate, which can be taken as y4, which is equal to y3 plus x3 divided by y3 into 0.2. So I can just find out the y3 value is 1.11692 plus 0.2 into 0.6 divided by 1.11692. I can find out the final answer is 1.22436. So this is the value at y equal to 0.8. So at 0.8 we got the value as 1.22436. Now what we have to do is we have to find h at when h is equal to 0.1, we have to do the same operation, the same step for the h is equal to 0.1. So again I can take this method, that means the y of 0.1, which is equal to, that means taken as y1, which is equal to y0 plus x0 divided by y0 into the time step. Time step is now 0.1. So I can just substitute the values of is 1. This value will be 0 and this value will be 1. I can get the value as 1, and then I going to find out the value of the next iteration is 0.2. That means I have incremented the value by 0.1, so that I can get the y2 value is y1 plus x1 divided by y1 into 0.1. So that this value y1 value is 1 plus x1 value is 0.1. The time step is 0.1 divided by y1 value is 1.0, so that the final value is 1.01. So that is the value of y of 0.2. Similarly, I can calculate the 0.3, that is taken as y3, that is equal to y2 plus x2 divided by y2 times of 0.1, that is time step. So y2 value is 1.01 plus the 0.1 times of 0.2, that means the x1 divided by y1 value is again 1.01, which is equal to 1.02980. So this is the value at the point of 0.3. Similarly, you can calculate the 0.4, that is taken as y4. The final value, I just repeating the same steps, just changing the values of y1, so the y2 and y3 and y4, everything. So the final value of 0.4 is 1.05893, and if you are doing it for 0.5, that means taken as y5, which is equal to 1.09670, and for y of 0.6, the final value is 1.14229, and for y of 0.7, y7, which is equal to 1.199482. So this is the value for the 0.7, and finally at the point of 0.8, you got the value as 1.25341. So this is the value, and the previously calculated value is 1.22436, and the time step is 0.2. Now the calculated value, when if you are taking the time step as 0.1, the final value is 1.25341. So we have to find out the exact solution of this equation, dy by dx is equal to x divided by y. So the exact solution is, so that is y is equal to square root of x squared plus 1. So this is the exact solution of the corresponding equation, so that I can just substitute the value of x is equal to 0.8 at x is equal to 0.8. So is the exact value of x is y equal to 0.8, that's whole square plus 1, which is equal to almost equal to 1.64, which can be written as 1.28062. So this is the exact solution. Now we have to find out what is the error. So the magnitude of the error, in the solution, or at h is equal to 0.2, we have the true solution as the error is the exact solution 28062 minus numerically obtained solution is 1.22436. I can choose 1.22436. The value is 0.05626. So when if you are using the h is equal to 0.1, the obtained value is 1.25341, so that the error is 0.02721. So now we can see this when you are using the h value as 0.2, your error is somewhat maximum. Then if you are using the h is equal to 0.1, you can forget the reduced error. Suppose if you are reducing the h values further, then you can get the values which is closer to the numerically analytically found solution. Okay, so that's all for this video. We have seen this the higher order methods in the I already told you that this Euler's method is the first order method and first derivative method. So you can just find out the solution which is approximated to the first derivative of the Taylor series, and then if you want to get the accurate solutions, then you have to manipulate the h value or vary the h value. And suppose if you want to get the more accurate solution than this, then you can go for the other methods, which we can see in the next class. Okay, so if you have any doubts, then again we can discuss it in the online class. Thank you.